So really understanding the pros and cons for some of these types of techniques. My contact information is on this title slide. So Adam T at NVIDIA.com. And if you use Twitter, it's Adam Likes AI. I'm always kind of impressed that out of a company of 16,000 people, I'm just Adam T. And I somehow managed to get Adam Likes AI as a Twitter handle. So anyway, that's neither here nor there, but one thing that I always chuckle about. So first of all, let's start with a big question. How long is this talk supposed to be? I had some ideas, right? Because, I sort of have done these before, so I have a fundamental understanding of how long these talks are going to be. But at the end of the day, I just didn't know. I didn't know how long this talk was supposed to be. So I decided to ask 4 different people. I decided to ask on the far left, my son, Reese, who can't talk because he's only 7.5 months old. But nevertheless, he's a pretty good, let's just pretend like he's right a lot of the time. And then we have John Stressing with his beautiful picture, right there, who is vice president of the Young AFCEANs and was sort of my Sherpa through this whole presentation. We would all suspect that John knows the correct answer for how long this talk should be. So I decided to ask him too. Third, I decided to ask my dog Pepper, who's dressed as a princess. She guides our life prior to my son being born, so maybe she'll have some input. And then finally, I decided to ask, one of these smart home devices. So one of these Echoes, Google Home, they're typically right. Sometimes they're wrong, but typically right. So before we start, we all know the answer, right? We know this is an hour-long presentation with questions. And so, this is one thing to keep in mind, is that when we're trying to solve these problems, when we're trying to train a neural network and deploy that neural network, we know what our answers are. So this is part of the known outputs equation. We also know what our inputs are, right? We have 4 inputs in this case. We have the opinions of my son, John, my dog, and a smart home device, right? But to be fair, I don't want to play favorites. I have an inclination that John is correct, but what if Pepper's correct? John may say, I don't know, we've done 3 hours in the past, but this particular talk could be an hour. So we don't want to play favorites. So let's try to be as charitable and equal as we can possibly be. And let's randomly assign each source a different number of votes. And so just like with any other voting system, the choice or the decision with the most number of votes wins, and they get to say. So in this case, all of these votes add up to 20, and this is just to make some of the math simpler. And I know, don't get scared that I said math because this is non-technical, but this is just to sort of ground you in sort of the total number of votes that can be attributed here. The fact that these equal 20 is completely irrelevant. The fact that the votes were assigned this way was completely random. So nevertheless, don't put too much credence in this whole idea of 20 votes. So right now, we have this, our network has been, sort of set up that my son has 10 votes, John has 1 vote, my dog Pepper has 6 votes, and this smart home device has 3 votes. And then we also have to remember that each of these sources has a guess. So I asked Reese, and Reese, my son, has no concept of time. He can't talk, so we're pretending like he can talk. And he emphatically shouted out, 2 days. So, if Reese is right, shoot, like, you guys better buckle up and, get your sandwiches ready because we're in for the long haul. I asked John, and in his infinite wisdom, he said an hour. And we know that the correct answer is an hour. I asked Pepper, and she was completely unhelpful. She just responded with a lick. And then I asked my, Amazon smart home device, and I'm not saying the name because it's right next to me, and it's gonna start answering if I actually mention it. And it said that a typical tech talk is 30 minutes to 45 minutes with questions, which seems pretty reasonable, right? But remember, we know, I'll mention again, we know who's right, which is John. So let's ask our network, how long is this talk supposed to be? 2 days, right? It's 2 days because if we remember, the source with the most votes, which was 10 votes, was my son, Reese, who said 2 days. And so that's our choice. That's the choice of our network. So we need to figure out how far off our guesses were. So this is the idea of calculating error. But remember, again, we know who's right. So we have known inputs, which are, you know, these 4 sources, and we have known outputs, which are what we fundamentally want to solve. And so since we know who's right, let's look at these votes again. So again, the randomly assigned votes that we started off with were 10 for Reese, 1 for John, 6 for Pepper, and 3 for the smart home device. And what we want to remember is that John is right. He's got a little heart on his face. And so we want our votes to look something like this. So remember, all of our votes added to 20. So again, this is where the math getting easy came into play. So we want John's number of votes to be as high as possible, and we want each number of, it's got a question from Jessica saying, which slide am I on? On each source has a guess. So I'm on a slide that says we want our votes to look something like, and it has Reese with 0 votes, John with 20 votes, Pepper with 0 votes, and that Alexa with 0 votes. Can anyone, is everyone on this slide? This the Zoom thing might be updating slowly.
No.
Yeah,
hey, Adam,
that's
this is Devin. If you're using 2 monitors, you may need to reconfigure things.
Okay, let me stop sharing. And I'm sharing an actual monitor, so let me stop this share. And then, sorry about it, guys. And then I will go to share screen, and I'll just do the PowerPoint. Okay. So just to, thanks for that question. I'm glad I had this up. So let's play from this current slide. Okay, so can you all see how far off were our guesses?
No, it says
Okay,
Adam
so
Thompson has started screen sharing. It's not showing the slideshow.
Okay. A little bit of latency in here. You see it now?
Nope.
All right. Let me try. Let me try not to share the PowerPoint presentation. And I'll just go like this. Okay, I started to share again. Can you guys see it now?
So you see the first slide of how far off were our guesses.
Okay, cool. So if I
okay, there's the heart. Now I see the heart. Now that makes sense.
All right, I'll drive like this. Yeah, I'll drive like this. Sorry. Thanks for letting me know. I'll make this a little bit bigger. So hopefully this works a little bit better. You know, I had all these like funny things in here. I was like, why isn't anyone chuckling? I guess you're all on mute, but you know, this is part of what we deal with these remote things. So we'll back up a little bit. And again, this was we're going to the initial ask of the network. We started with these votes, which each source has a guess. So remember, my son said 2 days, John said 1 hour, Pepper just licked me, and then the Internet of Things device said 30 minutes. And so we ask our network, how long is this talk supposed to be? The answer is 2 days, right? Because the choice that we went with was the choice associated with the most votes of, you know, our given input data, which was my son, who had 10 votes, and his choice was 2 days. And so what we have to do, just to double check, can you guys see the how far off were our guesses slide right now?
Yes.
Okay, great. So we need to figure out.
If you go to slideshow, you can still get your presentation.
I was doing that, and the slides were like really slow to update. So I was just trying to do this way to hopefully everyone can see this as it updates. So here, let me try to make it a little bit bigger. I can make this go smaller. And then I guess I can get this note section down. There we go. So we know how far off our guesses are. And we have to remember that we want, John to fundamentally be right. So if we look at our votes, what we want to happen is that we want our votes to look something like this. So we want all of the wrong answers to have 0 votes, and we want our right answer, in this case, to have 20 votes. So you want to maximize the result that is correct, and you want to minimize your scatter incorrect. And in this, we can look at our total error. So we're just going to do a subtraction here. And so we want my son to be 0 votes, and he started with 10 votes. So we know that he is 10 votes too high. We know that John started with 1 vote, and we want him to be 20 votes. He's 19 votes too low, right? So he needs to move in the other direction as Reese. We know that Pepper started with 6 votes, and we want her to be at 0 votes. So we know that her decision is 6 votes too high. And then the smart home device is 3 votes too high, because again, we want this to be 0 votes. So it's a pretty simple thing. Again, you know where you started, you know where you're going towards, and you want to minimize and maximize the total number of votes that each of these input data types gets in the decision. So we need to adjust these votes. So we need to make incremental adjustments with respect to the total error and the direction of movement. And so this is a lot of words. All that this is really saying is that as we train these neural networks, we want to make small changes to the total number of votes. We don't want to go, from Reese having 9 votes to Reese having 1,000 votes, and then you've way overcorrected, and then you have to swing back the other direction. And so what you do is you do tiny little nudges to the number of votes that you do. And you adjust this to something called a learning rate. So this is more of an advanced topic, and so I just mentioned this learning rate, just for completion. But essentially what you're doing is you're multiplying your votes by a little nudge. So say 0.5 or 0.6. So each time you update your network, these total number of votes changes. And again, remember, we started with randomly assigned votes. We know where we're going, we know what our total votes are, and we know the direction that we want to optimize. So you can use all of this advice in conjunction to train a network. And so how long is this? So let's readjust our votes. So Reese goes to 9 votes. He went from 10 votes to 9 votes. John went up to 5 votes from 1 vote. Pepper went down from 6 votes to 4 votes. And the smart home device went from 3 votes to 2 votes. So our votes have changed a little bit, right? But if we ask our network, how long is this talk supposed to be? The answer is still 2 days, right? And the answer is 2 days because my son, still has the most number of votes of all of these at the network, which is 9. And so we need to look at our error again. So in this case, Reese, we still want him to be at 0 votes, so he's 9 votes too high. John, we still want to be at 20 votes, so he's 15 votes too low. Remember, his vote had updated from 1 to 5, and we want it to be at 20. Pepper is 4 votes too high, so this is improved, but she's still 4 votes away from 0, and this smart home device is still 2 votes too high. So we're moving in the right direction, but our network is still wrong. If we ask this trained network how long our talk is supposed to be today, it's going to say 2 days. So again, to stress here, we're better, but we still are wrong. And so we need to readjust these votes again. And so let's do that. So again, we make an incremental change, which is affected by this learning rate. Again, don't worry too much about what the learning rate does. Just know that it nudges these votes. So now we've reassigned our votes to be Reese has 0, John has 15, Pepper has 4, and the smart home device has 1 vote. So if we remember, the ideal situation for our trained network is 0, 20, 0, 0 respectively. So with John was 15. But if we ask this network, so our network has been trained, if we ask this network how long should this talk be, like we do here, the answer is 1 hour. So we're correct, right? There's still a little bit of an error, so it's not perfect. But nevertheless, we've trained a network through this example that if we have the question of how long does the technology over bagels talk need to be, at the end of the day, our network goes and it asks John. So we just train a neural network. This is all a neural network is. You know, this step through this example, and I like to mention it because this has a firm understanding in what we do on a day-to-day basis as humans. And I think this is like really impactful for any of you who have had kids, is that when you're teaching kids right and wrong, when you're saying don't touch this, but do touch this, you're basically training their neural network. And so, you know, the decisions are all, you have known inputs and you have known outputs. So when you're looking at applications for problems that you care about in the field, if you don't have known inputs, like if you don't know what your data is on one side and you don't have known outputs, so you don't know what that data is called or is structured as, and we'll go into more detail about what that specifically means. But if you don't have known outputs or known labels, deep learning is not a good solution for your problem. So this is critical, and I'll continue to repeat this. Another key component here, reflecting on what we've done, is we trained our neural network by starting with random votes. So we just, we threw spaghetti on a wall. We said, we think that this input is going to produce output that we care about, and that may not be the case. And through the process of training, which is tracking how far off our guesses were and nudging our total votes in the direction of what we want them to be, we were able to optimize a correct decision. And then, at the end of the day, our neural network is trained to just ask John, how long talks should be. So I'll pause there and ask if there's, any questions before I continue on. I hope that anecdote was helpful to giving you like an intuitive idea of kind of what's going on here without touching, anything kind of heavy in the technology or math.
Hi, John, we see you.
Okay. Without going deep in the technology or math, how easily can this be done in C and C++?
Great question.
That is a good question. So we'll talk about this a little bit later, but the predominant language of the data science and deep learning community is interfacing with these types of libraries from the Python layer. And so fundamentally, looking at the software stack, the way that NVIDIA supports some of these frameworks that you train in. So now that we've kind of gone over the example of how you intuitively train a neural network, we need to put some code behind this, some computer code. And a lot of the way that people train these networks are with things called deep learning frameworks like TensorFlow or PyTorch. If you've heard of those, Caffe is another of these frameworks. And so they have a couple layers that you can actually hook into to training these types of things. So long story short, the vast majority of the research, the vast majority of the examples is all at the Python layer. But you can also hook into the C++ and CUDA layer to build these systems if need be. One point is that the deep learning community in particular is, it's fast moving, and it's a lot of open source, a lot of predominance in the open source community. So it's a lot easier if you say there is this network that I've heard about that does object detection. And if you don't know what object detection is, we'll get into that a little bit later. It's basically just drawing a box around things that you care about. That you can pretty quickly deploy that by cloning someone's GitHub repository and deploying it on a GPU. So there are certain advantages in terms of programmability, in terms of reuse and deployment that exist at the Python layer. If you're more comfortable with lower level, that's fine. But the general recommendation, at least to a broad community, is Python. if you even have to touch Python. We're going to go through an example where you don't have to even touch code.
Fair, thank you. I use Python, so thank you.
Yeah, no problem. I'm going to move on to
Adam, we've got a couple questions from Craig Zimmerman. One, is this called supervised learning? And then two, are the specific models, frameworks for are there specific models or frameworks for signal processing?
Yeah, so this is supervised learning. So supervised learning is when you have known inputs and known outputs. Unsupervised learning is when you don't have known outputs. So an example here is, expanding on the example that we already gave. If you're trying to classify, dogs from cats, that's supervised because you could have a lot of pictures and you could look at it with your eyes and you can say, okay, well, I know this is a dog, I know this is a cat, et cetera. So you could train a neural network on a large corpus of data to classify dogs versus cats. And known inputs, known outputs, that's all good. That's all kosher. Deep learning works really well there. But say you have a lot of IP traffic, so say like net flow data, or you're just looking at network logs, and you just see a whole bunch of IP addresses. So you have some knowledge about what the graph of this traffic looks like. You could know that this IP address talks to this IP address, but fundamentally it's kind of difficult to label that data. Same thing with signals data. It's kind of challenging to actually label data in a signals environment. And so you can do what's called unsupervised learning, where you do more traditional machine learning rather than deep learning techniques, which is looking at how that data naturally clusters, and there's different algorithms for that. And so once this data kind of groups together based off of some optimization routine that you do, then you can tell differences in, say, good versus bad activity based off of how they generalize. At the end of the day, whether it's supervised learning or unsupervised learning, I think a good thing for the broad community to remember is you're just trying to find structure in data. You're trying to find what's the underlying, like common thread that I can make generalizations for. And, this actually really transitions well into some of the fine print and assumptions along the way. And Craig, I'll hit the SIGINT framework question here in a little bit. And some of the fine print in here is really digging into the weeds. It's the importance of intuition. So we immediately as humans have been trained with our past experiences to know, in the case of how long should this talk be and the data points that I use to define this decision, we know things like dogs can't talk, that kids have crazy conceptions of time, and that the experts know best. But the key thing is the neural networks learn these facts, right? So they actually learn little features in your data that produce behaviors that you want to replicate and to optimize and to maximize. The other thing here is that we need a lot of data. You need enough data to have your deep neural network to be able to draw conclusions about that data. So this means that data also has to be consistently and accurately labeled. If you're trying to delineate cats from dogs, it's really challenging if your data is labeled incorrectly. Like if you have a couple dogs and you say they're cats, then your network is going to take that for granted. And so your decisions are going to be muddied because of this misclassified data. Now, there's certain ways around it, and there's ways for all of these limitations, there's ways around it, but they do complicate the problem. And finally, we have to have a goal, right? So this is sort of the end game. Models are dumb. It's garbage in, garbage out. So the other thing here is, even though there are generalizability techniques, so things like transfer learning, where you can train a network that's trained on one problem, so classifying cars versus trucks, to classify cats versus dogs, the performance almost always suffers, and you have to do a fine-tuning type thing. So the big takeaways from this, if you don't take away anything else, It's sort of the idea of a neural network is not too much different than training a kid. And then the other thing is you need a lot of data, and a lot is hard to quantify, right? Is a lot 10? Is a lot 100? Is a lot 10,000? Is a lot a million? Examples, and to some extent it's an empirical science. You have to kind of try, and then you have to recognize that these models are dumb. They're deep learning isn't going to solve all of your problems. Deep learning is going to solve a problem that you understand well. And the idea is if you can take a non-subject matter expert and teach them how to do something in a small amount of time, then you could probably have one of these networks do the same. So for Craig's question with the sort of SIGINT community, I mean, I think that if you're familiar with the SIGINT mission, I think we've all had experience with standing on an ops floor of looking at analysts just staring at waterfall plots of signals, right? So you actually have people looking at collections in the field. So whether they're signals or whether they're videos from compound soaks or something like that. And so if you have an operator who's literally counting the number of people going into a building and out of a building, why can't we just train a neural network to do that for us? So it's automating away boring, and that's another key, a key thing to think about as you look at whether deep learning could be applicable to your problems. Let's see, go. So again, I guess I kind of, I hit on these before, but again, do you have a lot of data? Is it labeled? And can you get a non-domain expert to be able to do this mission for me? The other thing is that, this kind of ties into the NVIDIA story as well, is there's nothing fancy about these training these deep learning models that are unique to GPUs. And I'm going to put a big asterisk there because there are unique software optimizations. There's, GPUs are designed for parallel processing, which we'll go to here in a little bit if that's not familiar to you. But you can train these neural networks on CPUs. You can. They just take forever. And so the emergence of deep learning and why you saw NVIDIA, get to be such a strong player in the AI and deep learning fields is because this field was all sort of rejuvenated with the advent of a network called AFCEA. And so AFCEA won a computer vision competition, and it basically exceeded human level performance of identifying images. And it was able to do that by training a network, one of these convolutional neural networks, on GPUs. And it basically was able to train this network in months, whereas previously it took years. So it made it so, I always think about the Hitchhiker's Guide to the Galaxy, if any of you have read it. And you build this big supercomputer and you say, what's the meaning of life and everything? And it comes back, thousands of years later and it says 42, right? So that's terrible. You don't want to do that. So you want to be able to have interactive conversations with your data, which is really what GPUs introduced to deep learning here. So the advantages of deep learning is we can get high quality performance. Again, the models often exceed human level performance. We don't have this feature engineering technique. We don't have these subject matter experts in the loop. And then also the associated costs with all of those. So one of the things is that for traditional machine learning and for traditional data science, I came across this in the signal processing community all the time, and I'm sure it exists in computer vision and other, cybersecurity as well, is you have that like one guy or girl in the office that like all new algorithms go through. It's like you have this idea and they're like, well, ask Jane, and if Jane doesn't give the thumbs up to it, then it doesn't go anywhere. And so the idea here is that we don't have to look for little esoteric things in our data. We can just throw a whole bunch of data at a network, and we can say, this is what we want to happen. so that once we have this trained network, when we deploy it to the field and we're ingesting new data into it, it can make correct decisions without having to, hand design new algorithms, focusing on new images or new signal types that may come up. So another point on this is once the deep learning solution shows consistent performance, we don't need to label new input data on inference. So we'll go over what inference is here in a second. It's essentially once you've trained a network, you deploy that network to the field and you throw new data at it. So data that the network hasn't seen before for making decisions. And so deep learning is scalable and it's generalizable. So these are significant advantages of deep learning. Some of the challenges, we'll go over a couple of these challenges and I'll pause again for some questions, is that, neural networks aren't perfect. They lack context, and they fundamentally look for patterns, colors, and textures. So two of my favorite examples are these computer vision tasks, and it's that these neural networks get confused about whether, on the left, whether you have a fried chicken or it's a labradoodle, and on the right, it's a sloth or a pain au chocolat, right? So we fundamentally, as humans, can really quickly tell what delineates these four classes from each other. But neural networks, are kind of dumb. So they don't understand that it looks pretty silly to have a sloth in a plastic container. And it looks pretty silly to have a bunch of labradoodles in a bucket, right? So we are able to have, a little bit more insight into the actual problem at hand that neural networks tend not to have. And then some, less fun challenges. Again, it's all data dependent. So it's dependent on, if you have garbage in, you get garbage out, including biases. So I'm sure you've seen, some of the challenges of artificial intelligence with biases towards, particularly things like racial profiling and other challenges that, AI solutions are in a lot of ways only as good as the data that you give it. And so if that data is biased, then your AI is going to be biased. Data imbalance is another challenge. So, say that you say, hey, I've got this great idea. I'm trying to determine when this new nefarious radar signal comes in. And I've got a million examples of, overall signal data, but I only have 4 examples of, the bad Russian or the bad, Chinese or whatever radar signal. And so you could train a neural network. You could say, hey, I want to find whenever this signal pops up. But the problem is if we look at accuracy metrics and we look at this data imbalance problem, so thousands versus 4, if you always say that it's not nefarious, your accuracy, right, is like 99.5% because of this data imbalance. So there's ways to handle it, but the best solution is to try to have balanced data sets, to have equal number of bad things that you're looking for as good things that you're looking for. Another thing is it's purely empirical. So I think you probably have heard that AI is a black box. And, if we make a bad decision, it's kind of challenging to look into that bad black box to figure out, why that decision was made. So you see this particularly with the self-driving cars. If, God forbid, the car gets in a wreck, it's a little bit challenging to say, why did that car exactly get in that wreck? So, there's model audits that we can do, but a purely mathematical reasoning that is 100% accurate and confirmed is out of the scope of a lot of these, current state-of-the-art with AI research, and it's computationally intense. This is, one of the challenges as well. Just really quick, putting everything that I've said into one slide, we have 2 aspects of this, the training aspect and an inference or deployment aspect. Training is when we use known inputs and known outputs to determine relationships and optimize relationships to give us a result that we want. And inferencing is when we deploy this trained network to the field introduce it to pieces of data that the network has never seen before, and make decisions based off of the data that is being applied to this network for inferencing. So I'll pause there and ask if there's any questions. I've got like 2 slides going into some of the weeds on deep learning, and then I want to quickly transition to an example. I know that we had promised, actually deploying a network, and I think it'd be helpful for you to see what some of this looks like before continuing.
Well, sorry for the late join. I've been working in the area of 5G for some time, and obviously this whole issue of ultra reliable, low latency communications and that sort of thing is coming about slowly. But I see a real big impact to being able to scour like big data, the collection of that, and so forth. I don't know if you've spoken about that prior to me joining, or would elaborate a little bit on that. I just appreciate any type of input. I can see the huge challenges of all this. As more cars become connected, they have more data to share and store, and all sorts of issues with that anyway. So.
Yeah, that's a really good question. And sort of this is, bookending this deep learning thing, is that, ideally we have these large data lakes of storage, and, we need to have tools to effectively perform that ETL, for example. So NVIDIA does, and it's sort of not in scope of this particular talk. So I'd be happy to talk with you offline about some of the stuff. But NVIDIA has done GPU applications to general data science. So this includes, how do you GPU accelerate data filtering, joins, sorts, merges, traditional machine learning tools. So this is, K-means, linear regression, some of those types of algorithms. And then we've built on this with other domains. So I created and maintained and developed a signal processing, GPU accelerated library, which I'd be happy to follow up on here later. There's one for cybersecurity analysis. There's one for geospatial distances and transformations and that type of thing. And then we also work with partners who have built on top of our open source libraries to do things like GPU accelerating SQL queries from, an Amazon S3 bucket. So this is basically saying, I'm going to take the parallel compute power of a GPU and use the thousands of threads that are available for compute, and have each of those threads do, one element of a SQL query. So you parallelize something that's fundamentally serial. And so yeah, there's a ton. I mean, that's one of the challenges of this, is that there's a ton of really great information that we can go more into depth here. But this is focusing, this talk is focusing on just the deep learning piece. And, I'm going to skip forward here a little bit and say that this deep learning is one of the 3 pillars of accelerated data science. And so this data analytics, so ETL and understanding your data, and machine learning is all part of, at least majorly part of an initiative that we have at NVIDIA called RAPID. Which is GPU accelerated data science. So you can actually go to rapids.ai, that website, and get a little bit more information there. And again, just send me a note, and we can chat more about that.
Adam, I shared your email with Don. There's a couple other questions in the chat right now. One of them is from Matt Rommel. What is the most accessible way to begin experimenting with using graphics cards for AI parallel processing? Is there a cloud utility available?
Great question. So I'm actually going to go, there's some other stuff in here, but you know what? I just want to go straight to this example. So this is actually, what you see on the screen is a software product that we don't hear a lot from NVIDIA out of, for example, which is, I have a little bit of a problem with it, but I think it's a great tool to get started, and it's called Digits. And so I have this running on my workstation, but you can set it up on AWS, or you can set it, if you have a GeForce card at home, like just a gaming graphics card, you can set it up as well. We have a lot of the software comes from what we call the NVIDIA GPU cloud, which is this website, ngc.nvidia.com. And if you go here and you can search for digits, this essentially is a Docker container that says how to get started. So the key things, and I can send out some information. So just if you're interested in more information on how to get started from the Docker side, just drop me a note and I can put together a playbook of how to do this. But at the end of the day, you basically need to install a yeah.
We still see your slides. We're not seeing what you're doing.
Oh, thanks. Sorry. Let me stop share and share. Okay, can you see it now?
Yeah, we can see that now.
Okay, perfect. Thank you. So this ngc.nvidia.com has a repository of these Docker containers, and this is also available. This is replicated into ContainerYard, if that means anything to you. So you can actually, this is all in like Docker playbooks, for example. So this actually shows you the command that if you have the CUDA driver installed on your machine and you have Docker installed on your machine, and I can talk offline how to do that. And I say your machine could be a GPU in the cloud, it can be a GPU in your laptop, it can be a GPU in the data center. You just need a GPU here. So you can run this command, and then this starts up, it basically opens up an IP address to get to digits. So this is what digits looks like. And really what it is it's a really quick and dirty way to train a neural network on your own data, you know, and see results pretty quickly. So you wouldn't really want to do this for, you know, production. This is just one of those things where you're like, I wonder, I have a lot of data. I think it's well structured. I wonder if deep learning can be, you know, good for my problems. So what I've done here is I've already loaded data in here. And so, you know, I'm not going to do like a full-on tutorial of how this is structured, but I have loaded data, you know, from a place in my computer. And so we can see here, if we look at this data, there's a total of 7,500 entries, and there are 3,750 negatives. So this is basically an image classification task where I'm trying to look for negative versus positive. And this is signals data. So these are spectrograms of looking for chirp signals. So what a chirp signal is this, I'm gonna look for a good one. So see, can you guys see my cursor? Looks like some nodding
yes,
head.
I can. I can see it.
Okay.
Yes, I can.
Cool. Perfect. So this little like linear, you know, ramp thing, this is what we're looking for. So this is a chirp signal. So anytime you see this in the data, that's positive, right? So that says a chirp signal is present. So we see one here, we see one here, and these are both labeled as positive. We see one here, this is positive. And you can see the signal to noise ratio has varied, right? And so what I mean there is that it's really bright, so you can see it really easily in this example, but it's a little bit less bright in this example. So it's kind of realistic-ish data. And then this, for example, in this example, this is negative. There's not a chirp signal present. And so this is what my data looks like. You know, this is pretty typical. This could be cars. This could be images of cars versus trucks, and the label is car, truck, car, truck. So this is my data. And now what we're going to do is we're going to train a network on it. So I'm going to go in here and say, I want to do classification, because I'm going to say whether I'm doing, you know, whether there is a chirp signal in here or not. I select my database. I'm going to say, just for the sake of time, I'm going to do 5 training epochs. So an epoch is when you adjust your learning rate. So it's when your entire data set has been introduced to your network, and then the error has been propagated, and you adjust your weight. So in the first network, we adjusted the weight twice. So there were 2 epochs in my, you know, like funny example at the beginning. I'm going to change this learning rate just a little bit smaller, just because I know for this data set, that's what I need to do. And then a lot of this is just kind of, you just keep it the same way. And I'm going to choose AFCEA. So AFCEA was the first deep learning network that existed. So we're just going to say, what's the baseline for this data set? And I'm going to select one of my GPUs. So I have, I have 2 Pascal, which are older cards. And then I'm just going to say signals. So these are just kind of tracking names. So then I say create. So this starts to train my network, right? So this is training AFCEA based off of the data that we invoked. And so what you'll see here is, the training time that it's taken, and then you'll start to see a plot. And so as this plot populates, you're tracking the epochs down here, and then you're tracking accuracy and loss, right? So we're saying how well are our guesses and how small is our loss. So we want our loss to be as small as possible. We want our accuracy to be as high as possible. So right now we've run almost 3 epochs, and our accuracy is at 98% accurate, and our loss is at 0.06, right? So this is, we've trained a network essentially. This is deep learning in action. And so we said only 5 epochs, so this thing's going to stop here in a second. And so it's done. And now we can essentially test, right? So we trained on a certain data set, and now what I want to do is test it. So I'm going to do data, and this is just where my data is locally, test data. And sure, I've done this before, so I'll just use this one. So this is just a random, I'm doing inferencing right now. So I'm picking a random, I know it's negative, right? So I can test how accurate it is. So this is a random image that doesn't contain a chirp signal that wasn't used in the training set. So this is another key thing, is that your training set and test set that you use to do this model have to be kept separate. And so I'm going to say show visualizations, and I'm going to classify. So this is running inference right now. So this is passing this data through the network to determine whether it has a chirp signal or it doesn't have a chirp signal present. And the other key thing here is that we know, since we pulled it from the negative data set, that it doesn't have a chirp signal in it. So we can see here with this prediction that the network is 97% confident that this does not have a chirp signal in it, and roughly 3% positive that it is. And so we can see here with our eyes that our network was in fact correct. And then these are some of the just troubleshooting. This is looking at the actual features that the network honed in on to determine whether this was or wasn't a chirp signal. So this is a trained neural network, and it was done with no coding, and it was done, I guess 6 years ago. This was state of the art. And so digits is it's a nice way to get started. Again, you have most of the community that's run at the actual Python layer through something like PyTorch. But nevertheless, this is, pretty easy, right? If you have data, you can just, click buttons and see which gets you, the best results as quickly as possible. So I unfortunately have a 1 o'clock hard stop. So I just wanted to, I wanted to pause there and see if there were any further questions. I wanted to get to basically what the GPU versus CPU was, and all that good stuff. But I think with time constraints, it looks like that's not going to happen today.
Hey, Adam, we had a question from a couple of minutes ago from Ross Beasley. How is time varying context incorporated with the fixed models used in the fixed production context? Things change over time.
Yeah, so time's hard. So there are different types of networks. This was just one example. This is a classification network. You have different types of time series networks called recurrent neural networks. So if you've heard RNNs or LSTMs, those have a temporal component in it as well. But making use of time is one of the big research topics, particularly in folks working on SIGINT, right? It seems we need to have memory of time to make correct classifications, particularly for things like modulation recognition. But nevertheless, yeah, I mean, the quick and the dirty is it's looped into things like recurrent neural networks, but it's still an active area of research, which is a limitation of deep learning right now, is for time series data.
Awesome, thanks, Adam. Craig Zimmerman had another question a couple minutes ago when all the chirp pictures were up. What are the image sizes?
So in this case, the image size is for AlexNet. AlexNet expects 256 by 256. So I basically cropped, you can squash the image to match that size, which was handled by digits. So if I actually go back and I do like a new classification model, you can see here, GoogleNet, your image size needs to be 224 by 224, AlexNet 256 by 256, and LENet, this is the handwritten digits classification network done by Jan LeCun, was 28 by 28. And you can edit these. So if you choose AlexNet, you can customize, and then this is TensorFlow code, so you can actually get into TensorFlow and do any sort of transformations that you need to do up front. So a lot of this, again, this goes back to one of the questions earlier, I believe from John, saying, can you do this at the C++ layer? Again, you can, but if you peel back the onion on some of this stuff, you're just hitting Python, which is just hitting C++ and CUDA at the end of the day.
Okay, does anybody else have any questions, any comments, any input? Was this helpful?
This was nice. Thank you, Adam.
You're welcome. You're welcome. Well, it's great talking to you guys. I really appreciate the opportunity. Again, don't hesitate to reach out. It's just adamt@nvidia.com. And unfortunately, I gotta run here in a second. But really appreciate you guys taking the time to learn more about this, and looking forward to following up on some of the great things we talked about today. So appreciate it, and thanks, John.
Thank you, Adam.
All right.
Yeah,
Cheers.
thanks a lot. Appreciate it.
All right,
You're
I'm
welcome.
putting Adam's email and my email will be in the chat box if you just want to copy and paste it on your way out.
Thank you, Adam.